And the first thing we have to know is, of course, again, how individual devices behave and how reliable they are. Also, we will see what influences on reliability will be. And in some later sessions, we will learn how to combine such information to predict more complex systems. Okay. Yes, my background in industry is automotive industry. In fact, that is not the latest Mercedes car, but already, let's say 10 years ago, there was a very large trend towards more electronic systems in cars. Nowadays, it is said that a typical Mercedes has roughly 100 microcontrollers in it, or these are part of a so-called electronic control unit. And these, again, are very often combined with some sensors or actuators, for instance, for lifting windows. But when you have a window lift electrical, you need a sensor in order to avoid clamping someone. And in that way, systems become very, very complex. So here are some examples: headlamp leveling device, distance warning radar. I must say I have a small smart car, and even that has a distance warning radar, which is also used to control speeding up, or better slowing down of the car. Then we have oil quality sensors and oil level sensors. These are often combined. In fact, there has been a quite long development until really functional oil quality sensors were used. Then we have accelerometers. These are devices which give a signal on the basis of which the front airbags, or also nowadays side airbags, are released. And we need also, in connection to that, seat occupant detector, because when, for instance, when we have a children's seat on the passenger side of the car, that airbag must be deactivated, and in that way we need to know occupation of such seats. We have a smart rear view, so in order to avoid being blinded by the car behind us, in former times we had to switch mechanically. Nowadays, that is done electronically. We have a rollover sensor. We need that when a car is rolling over because it lost the track, for instance. Then the engine must be shut off immediately. And based on the signal of that rollover sensor, that happens. Also, on the other hand, we have a tilt sensor that has several purposes. One of the purposes of a tilt sensor is when a car is stolen. Sometimes the car is towed up to a van, yeah, and so we have a slope. And when the car is not driving by itself, but when it is going up a slope, so it is tilted, then, for instance, an alarm signal can be activated, or a signal can be given via a smartphone to the owner of that car that his car is moving. Of course, we need wheel speed sensors for anti-brake locking system. That is something which we have now for, let's say, 30 years or so. And then we have lots of electronics in the engine, for instance, measuring the airflow into the engine. Of course, we do not need that for electro vehicle, but in that way, there are very many systems. And one of the companies, for instance, in Germany, and again, more than 30 years ago, was BMW. They put in lots of electronics. And at that time, also BMW had they were very fine cars. Yes, they had a very good image, but the quality was low. Yes, there were often breakdowns of the car on the autobahn or on road due to problems with that electronic. Until after several years, they had improved the reliability of the electronics so much that the quality of the car was not lower than that of a car which was purely mechanical, you could say. Still, you can see that when you look for the statistics of cars breakdowns. Presently, Mercedes is not the best. Yeah, in former times, Mercedes was always best, but nowadays they are not, and partly that is due to the the high content of electronics they have. Yeah, it's quite evident. The more parts you have, the higher the probability that one part will fail. And that's a very simple reason why when you put in much electronics into a car, of course, you must increase the individual devices' reliability in order to avoid that the system reliability goes down. Okay, later on we will see that also on a mathematical basis, and we will see how we can predict the reliability of such systems. So a car, typical designed lifetime is 10 years, now maybe 15 years, 300,000 kilometers. We often have integration of microelectronics into mechanical components. That's so-called mechatronics, and that leads to more load on the electronic. We have temperature environments, especially on the combustion engine or in the gearbox, going up to 200 degrees centigrade. We have vibrations and mechanical shock. We have what's also important, aggressive media, oil, dust, also the cooling liquid has a certain aggressiveness, and something I forgot is one of the most aggressive is the brake fluid, which is a hydraulic oil, but it is very corrosive. Okay, so there was a large development. Here are some examples. Already in 2005, there were proposals of telemetry systems where the car would analyze itself and see, oh, I don't feel well, and I give notice to some service point, and they can be prepared for that. So that were first ideas we had seen in research, and also such telemetry systems were installed also for security reasons. In America, they have that for a very long time, probably for more than 10 years or so. Then there were more systems which were aiming at high reliability. One is X-by-wire. X means any function you have in a car, and of course, what we have for quite some time is acceleration by wire, braking by wire. Not yet really steer by wire. and that requires very high safety. Also, it requires not only a unidirectional control system, but it also needs some, for instance, feedback of the system to the driver. Even steer-by-wire requires very high reliability and very high safety. Of course, you don't want to drive on an autobahn, and suddenly your steering wheel is just loose, you could say. Yes, no more feedback to you. You give no more feedback to the car. So not such a good situation, and in that way, it would require extremely high reliability. Now we are some steps ahead. We are going towards autonomous driving functions, and these require also very high reliability and safety level of the car. Okay, when we look at traditional cars with a combustion engine, we can say there we have several environments. One environment I already omitted, that's the passenger compartment. And here we have the normal area and we have the dashboard. And then we have the classification under the hood. There it can be quite warm. The specification says to minus 40 to 125. So 125 is the maximum the cooling liquid can have in a car. It's under pressure, so it's not the boiling point of 1 bar, but it's the boiling point of maybe 2 bar or so. And here we have vibrations of up to 3 G and shock of typically 20 G. Please note, these data are, let's say, they are taken as the maximum that can occur. Then we have on the engine, of course, here it can be hotter due to the direct contact with the metal parts, which are in contact with the combustion. It goes up to 150, and sensors on the engine, they are still closer to where something happens. They are specified somewhere up to 175 degrees centigrade. Here, the cycle numbers are given as 3000. So that means it's a driving cycle. So how can we get that? Let's say I drive to the university in the morning. That's one cycle. I drive back in the evening, second cycle. So then I do it on 200 days per year. And that means 400 cycles in that year. And over the time, at 8 years or so, I have achieved 3,000 cycles. So that's the idea how it is computed. We have other cycles. For instance, when you drive a car in a city traffic, yes, and often you have stop and go traffic, and that can mean the temperature in some sensor, for instance, goes up and cools down, and after a few hundred meters, again, the same cycle. Typically, these cycles do not have such large temperature swings. The temperature swing is lower, but it can be there, and we will also have to see if what is worse, many small delta T or only a few very large delta T. We will later on come to that. Okay, here's an example. Some colleagues of mine, I was in Daimler company. they were close by in the Unimog works, and they designed a new gearbox, and they wanted to know what the temperature of a certain sensor will be if it's mounted directly on the gearbox. And they put some temperature measurement on that Unimog car, and they made a test drive. And here you can see that gear oil goes up to 100 degrees centigrade. That means alone the environment of the electronics can be so high, but in addition, of course, we can have the self-heating of electronics. On some test point, so that were some, let's say, some screw holes where the sensors were screwed in, the temperature swing was not as high, but we have temperature swings going up to, let's say, from here to here, up to 40 Kelvin. Interesting is also here that's, I think that measurement was made in March or so, or April. The temperature changes, and that was because they made that test drive through the Black Forest. So if you are lower in the Rhine Valley, it's warmer, and every 300 meters you go higher, the temperature decreases by roughly 2 degrees. So, okay, so that was the situation. So important is you cannot say in reality the environment is constant, or you have a constant swing between two environments, but it is more or less stochastic depending on how the car is operated. Okay, another thing which shows us that it is important to take into account temperatures from two sources is this here. In former times, the fan of the car was driven mechanically, and it was running all the time. Of course, that causes you a few kilowatts of power. Yeah? Later on, I have a 50-year-old Mercedes. They had a Visco clutch, and that was only activated when the car was hot. Then some fluid was expanding, and then it clutched, and then the fan was running. So that was something you could say an intelligent mechanical solution. Later on, the fan was driven just by a two-point control, yes, on or off electrically, and it was an electrical fan. And we had then a development of bringing in power electronics, and that was the first version. So here we had a electronic control, and now you must keep in mind that the temperature of the fluid can be up to 120 degrees centigrade, roughly a little apart from the cooler. It's maybe only 100 degrees centigrade, but that's the environment. On the other hand, we have here the electronics. We have power here we see them power semiconductors, and also we have big capacitors. But here we have a control, and the speed of the fan is adapted to the thermal situation we have here. Now, if we look at, we can say the maximum temperature in the critical part of that electronics is the environmental temperature plus the temperature increase, and the temperature increase is something like the dissipated power multiplied with the thermal resistance. And now the question is, what is the dissipated power? We must say the power of such a fan is a kilowatt or so. And then we can have a power dissipation altogether going up to 5%. And 5% of a kilowatt is 50 watt. In fact, in the total system, we have higher losses. Here they calculated based on electrical simulation 60 to 70 watts. And that again leads to a maximum temperature in the electronics of 144 degrees centigrade. And maybe that can be above the limit of the semiconductors, depending on how they are specified, but it is definitely above the temperature limit of electrolyte capacitors. Yeah, these are normally not specified for so elevated temperatures. So what can you do? Of course, you can keep them cooler than the hot spot, which is here at the semiconductors. Okay, that is that's telling us we have to take into account not only the environment, but also what develops from the operation. Okay, now we have an overview of temperatures which we can find on the site where electronics is. Here they specify on the dashboard, it can be up to 110 degrees centigrade. Dashboard normally is black. If you have sun on it, it can be extremely hot, or sometimes you cannot even touch the steering wheel, so hot it is. And when you have electronics then, and now you have lots of electronics in your display system, then the temperature can go significantly higher. On the throttle, it goes up to 200 degrees centigrade, a little further apart from the engine, maybe 120. Often it is a problem, not the operation, but when you shut down the car, you normally, in most cars, don't have any more cooling. Yeah, but so the heat which you had and which was taken away now distributes. That's the reason why you nowadays see cars, they are closed and shut down, and anyway you can hear a strong fan in that car, and that's just the reason to remove the residual heat you have. Okay, on the exhaust itself, you have up to 650 degrees centigrade. Yeah. Is the highest temperature in the car? Which? No, the highest, of course, is in the combustion engine, but you do not put a sensor there. For many sensors, you can put them a little apart. For instance, if you measure pressure, you do not have to put them really into the combustion room, but pull them back a little, and then they are already in the cylinder head, for instance, and the cylinder head is cooled. Yeah. So so it's depending very much on the situation, but on the other hand, when you put it further into you can also have such temperatures here. Okay, so that just shows us temperatures are very much different depending on the location. High temperatures of the environment, power dissipation is important. Then we have accelerations. And both harmonic accelerations, which is called vibrations, and mechanical shock, which is that here. And then we have humidity And as a result of temperature, we must say it's the temperature alone, it's the temperature swings we have, and it can even be the speed of temperature change. That all leads to thermal mechanical stresses, and all of these changes are variable and transient and not constant. So in fact, one of the reasons why Mercedes were so successful from the 1960s on and had the best reputation of reliability was that I think they had the best team for measurement and data acquisition. They even had a small factory for building their own instrumentation equipment. They really had production lines and development lines for instrumentation and just for test drives, not for series production, just to find out what happens in a car. Okay, now let's go to a car. I took some more data. It's not so easy to get to know what happens, but here it's the German Automobile Club published in 2022 some statistics of cars breakdowns and the reasons for that. One of the most important reasons is the battery, empty battery. But it's not only the battery's fault. Yes, one thing is a battery has a limited lifetime, and that's significantly shorter than the lifetime of a car. So in a normal car life, you need at least 3 batteries, I would say. So it's a wear out part. Yeah. Okay. And if someone doesn't care about the wear out, it's like you neglect your brake pads are worn out. Yeah. That's also not the fault of the brake. Yeah. Okay. So you could say battery is most important. Car doesn't start when it's on a cold day mostly. Then what is important, and that always has been since that BMW problem, motor management. You know, if something's wrong here, often the car just refuses to act further on. So it's not only that it doesn't work, but the car sees I have a problem and I shut myself down. Yeah. So then we have body, suspension, drive, which can make problems and has a high portion of electronics now. And then what is important, generator, starter, lighting, and cables. So you could say when the generator doesn't function properly, the battery will be emptied. Okay, tires is a certain problem, fuel system also a little, cooling, climatization. What is not in here, of course, you don't call the ADAC if your car radio doesn't work, yeah. But it's also a problem, and there are other statistics, for instance, in America by J.D. Powers. They also take into account such things like audio or information system and so on. Because if it makes a problem, you go back to your dealer and have it fixed. Okay. Now, an important part in such a car is an electronic control unit. Maybe here you can see such one or such one. That was the one on the side. That was the one integrated here on the motor itself. So that's a control unit. What does it have? It has instrumentation. It has access to sensors. It has power electronics. And of course, it has a microcontroller in order to build up some control loop and yeah. And so I think they still have 8-bit microcontrollers for some applications. Of course, trend went towards 16-bit or higher, but in the end, we have these electronic control units, and here that's an example of one I did investigate in 1999. That was just my last year in the company, and at that time, just by chance, I had access to many failure data. Now, when you as a researcher want to have access to such data, you will not get it, yes. In fact, on my job, my successor, he tried to get more data, yeah, inside the company, you have to keep in mind, and he didn't get it, yeah. Maybe he wasn't smart enough to get it, but for me, it's I would not say it's smart, but it was also by luck, and also I must say I was daring a little and just taking the data to make more evaluation. Later on, I took them with me, and now they are, let's say, a little out of date, but they are very representative, and I would say the general statement is still valid. Yes. The ECU, when it fails, it can notice itself that it has a problem. It has an ASIC on it, which controls the other devices, and also some error code is stored there. And based on that, you already have a good, let's say, pinpointing of where the defect is. That was quite some time ago, and that's still the situation. So in German, the Fehlerspeicher, or the error memory, is important. And now, when you look, when you have such a situation, you typically, the car manufacturer takes that part, looks what is an error code, and then he gives it to his supplier. So Tennick or Bosch, tell me in detail what happened here. And they have to investigate, and normally it takes quite some effort to investigate it. It's not just reading out some data, but maybe you have to take it under a microscope, under electron microscope, cut it, X-ray it, and so on, just to find out what's the reason for that failure. But in the end, we could find out for that ECU, which has a complexity like the one I was showing you, and it was an anti-brake locking system. Half of all of the failures were just failing devices we had purchased and soldered on the board. Yeah, so that's also a typical value when you have a system like an ECU. Components will have a high portion of all failures you will see, and that means it is very important what to purchase and from whom to purchase, and to specify correctly. Also, 20% of all errors or faults or failures were, no, not failures, but errors, faults were not reproducible. In fact, we wouldn't find out. But that can be, for instance, a problem if you have a bad thermal contact. Yeah, it heats, something expands, the thermal contact becomes worse. It heats more. Then the electronics say goodbye. They do not have to fail. You just, if you have your PC, just turn off the fan of the processor. The processor will work for 2 or 3 seconds, then it shuts off. Yeah. But if you don't know where the thermal problem is, or if there's a thermal problem, you cannot reproduce that really. Yeah. Sometimes it takes an hour or two of operation until that happens. So often it's not reproducible. Mishandling is also a problem. That can be, for instance, someone being electrostatically charged up and touching the pin, and then a CMOS device, but also other devices can fail. And now is something interesting. What we could find out, if you do a proper manufacturing, the portion of failure causes is very low. Yeah? Your production is under control, and you see that in that time, or coming from that time of production, which is typically you regard a quarter of a year, you can say in that quarter of a year, later on, you do not have problems, because you know for every part when it was produced, and you know also all of the production conditions, yeah, like soldering, oven profile, and what else. All that is stored. And now, when you have a problem, you can say, suddenly, the portion of all failure is as high as the component you purchase. On the other hand, you could also argue, okay, probably it's same for the suppliers of the components. If they have their production under control, the reliability will be high, quality, and if they don't have it under control, which can happen, reliability will be low. But as you have several thousand components on such a board, it's always a mix. Yeah. Okay. So manufacturing can be a problem. And now I took all the data and I just looked how the numbers of failures increased over the mileage of that car. The mileage was computed. We didn't really have it. It was computed based on, let's say, no, we had it. Sorry, we had the mileage because we knew the mileage when the car was breaking down. And so we can see many of the defects. You have a strong increase over the maybe first 10 to 20,000 kilometers. And then sometimes the increase, like for the yellow curve down here, is very low. Yeah. And that means you do not have a constant rate of failure, but somehow the rate of failure will go down over time. And that's something which we will still sorry. Now I got here some menu on my screen. Okay. Yes. I could do more investigations. As we saw, we have many devices on that board. For instance, we have a microcontroller, which is a 52IO device, surface-mounted device. We have a printed wiring board. We have a power MOSFET. That's a relatively simple device. We have a quartz. We have an ASIC. Interesting is when you look at the ASIC, it's a QFP, also a surface-mounted device with 66 IOs. So you could generally say the complexity of that ASIC is probably the same or higher than the complexity of the microcontroller. Yeah. So how many transistor elements do you have in it? Then we have some miscellaneous devices. We have a voltage regulator, also a TO device that does a complete voltage regulation, so keeping at 12 volts for the whole thing. And then we have a multiwatt, which is something like a power semiconductor ASIC, you could say. So it has many transistors in it, and we have capacitors. And for all of these, I have been computing the failure rate over these 40,000 kilometers. And I assumed, I think, 50 kilometers per hour as an average speed. So, in fact, these failure rates are really failure rates taken from operation of cars, which were breaking down within the first 40,000 kilometers of operation. And now what is interesting is the microcontroller has a failure rate of 240 fit, while the ASIC, which is as big as it, has only 60 fit. Yeah. So you could say, again, both are similar devices, but again, you can have a factor of 4 just from the manufacturer, from the maturity of the semiconductor technology, and so on. It's similar when you look at the power MOSFET. The power MOSFET is a really primitive device. The voltage regulator is similar. So one has 110, the other has 50. But the multiwatt, yeah, which is more complex, which does much of the control in your thing, it only has 20 or so fit. So again, that shows us you expect from some they should be more reliable because they are more simple devices, but in fact, it's not always the case. The capacitors have only a few fit, but on the other hand, you have to multiply that with the numbers of capacitors. Yeah? So maybe you only have 2 fit or 3 or so, but multiply it with 100 or 200, yeah, and then you get to say, the capacitors altogether are the worst part of that. ECU. What is also not good is the printed wiring board. Yeah? And now what is one fit? That's something which is very important for you to know. That is 10 to the power of minus. Normally it's given just per hour, but it's not trailing parts per hour, but it's better to say it's 10 to the power of -1 parts. No, it's 1 part failing from 10 to the power of 9 sample hours. That means you either have 1 million samples and you look over 1,000 hours, or you have 1 million hours if you have the time and look at 1,000 devices, or 10,000 hours and 100,000 devices. Yeah, and then one fails. And that is one fit. So fit is not an absolute value, but it's something like a probability per time. Yeah? That is really important. Fit is probability per time, and not absolute values per time. So it's a really low value, but in fact we have devices. Yeah, we can see but several fit, and how can we know such fit rates? In fact, only when we have very many parts in the field where we know about failure. The problem is that all of the parts together in the field are from different batches and different types and so on. So it's not so I would say justified to put them together. But in the end, validating so small fit rates is almost impossible, you could say, but we will see some tricks. Also, when I started that lecture some time ago, I addressed some manufacturers like the Bosch or some smaller manufacturers and like Micronas here. For instance, that magnetic sensor is from Micronas. The bulk micro machined the sensor IC that was from Bosch. Also, I think that was from Bosch here. And now we have seen it's important to look for the failure rate, and the given values for these different applications are very variable. For instance, if you have something from Bosch, you can say specifying it for 55 degrees centigrade, you can have on acceleration sensor fit rates of 1 fit. It's extremely low. When you go to 125 degrees centigrade, they specify already significantly higher temperature, higher fit rates of 32 to 49. Now you also give for such a fit rate a confidence level. The confidence level is important because it takes into account how many failures you used for computation of that failure rate. In the end, you can say, yeah, you have one failure in 10 to the power of 9 sample hours, and that gives you a failure rate of 1 fit. But you cannot really be sure that it's a failure by chance. It could have been later or could have been earlier. Also, you want to say, the customer wants to know, is it better than that? Yeah, he doesn't want to know, is it worse than that? So it's a limit, and you must be below it. And now, for instance, if you specify a low value of failure rate, you can only give a lower probability that this value is valid. Yes, when you say as a customer, I accept that it is specified with roughly 50 or 49 fit, I can rely more on it. Yeah, and in that way, we must give a so-called confidence level. The alpha is the significance level, so that's a probability of error, and the confidence level is the probability that that statement it is below 49 or 33 is true. Yeah, so we will see how we get these data, but in the end, also here is something interesting. That was from a small manufacturer, and he gave us conditions of testing, but they had no failure. And even for no failure, you can based on the effort of testing, you can specify a failure rate with a certain probability that it is true. But in fact, as you have no hard data of how it fails, or if it fails and when it fails, the values you compute here are relatively high. Yeah. Yeah. The confidence level is the level that the statement you take is true. Yeah. So I say, for instance, third line from bottom, 33%, 60%. So the confidence level says, no, you say the failure rate is below 33 bits, and I can rely on that statement with 60% probability. 60% is almost 50-50, you could say. Yeah? Do you really rely on it? Okay. 90% is something better. You can rely more on it, but then you must accept that the failure rate, you can only state the failure rate is below 49%, but on that statement, you can rely with a probability of 90%. And 100% minus 90% is 10%. So the probability that you are wrong and that it is higher is 10%. That's the statement, but it is also only valid. That's really important that all of the assumptions that you have taken for that statistical evaluation are true. Yeah? You can do that anyway, that calculate, but the preliminary assumptions must be true. Okay. Now, that were based on, you can say, data sheet. Another thing is, none of these devices were tested at the temperatures that were specified. Even Bosch couldn't test so much. So what is the trick? We have seen higher temperature, higher probability of failure, higher failure rate. And the trick is to test at high temperature, going up to 200 degrees centigrade, taking a failure rate, and then taking an assumption that the failure rate is lower at lower temperature, and then you need a model for computing the values down. What is a model for temperature dependency, generally in chemical and other processes? What's a standard model? Most simple, every engineer must know it. I insist on that. What's the name of the guy who found that model? It was in the 19th century. He was a professor in Sweden, I think. Stockholm also. What was his name? It was an idea coming from chemistry, but no, Kelvin was an Englishman. It was Arrhenius. He had a Latin name, and so we must know Arrhenius' law, and that says all processes which have an underlying chemical process, and that's also true for reliability processes or reliability limiting processes. All such processes are accelerated in an exponential way by the absolute temperature. And the temperature is in Kelvin. so you are 10% correct. but the name of the guy is Arrhenius. And again, I insist every engineer should know Arrhenius' law. Yeah, because it's the most significant temperature dependence we have on Earth, yeah, or generally. And okay, now there's some other information. Again, of course, I like more real failure data, like from my anti-brake locking system or here. That was an investigation in China. In application of electronics, Chinese are quite ahead, let's say. Yeah? In some regions, they are more modern than we are here in Germany. For instance, I only got an electronic electricity meter 6 years ago, and only because I built in photovoltaic in my house. Before that, it was purely electromechanic meter. Chinese had it before, and now they have only a few models. They have more or less a standard model, but they have also several climate regions. And here that's the more important climate region, and they have a database of 500 million devices. So that's already good statistics, even if you deal with one fit or so. In the end, it could show that meter had quite a number of submodules. Yeah, so we have the power module, we have a measurement module, we have a control module. Yeah, put in some display module, here also a communication module, because it can be read remotely via the internet, also storage module, and a security module. You put in some number so you can access it. So that's the module. And we look at the failure rates. They are between 40 and 481. In fact, that smart meter was not so really reliable. It has a failure rate of 1,882. And when you,
can you explain shortly the abbreviations at the top of each column?
I come to that. So the fit is the failure rate. Yeah, one fit is 10 to the power of -9 per sample hour. When you take the inverse of the fit, so the fit is something like 1 divided by hours, you get hours. And under the assumption that it is an exponential distribution, which we have seen in the first session, under the assumption that it's an exponential distribution, you just take the inverse of that fit rate and you get the MTBF or the MTTF equivalent here. That's the mean time to failure. And so when you have such a thing, you could say you as a single person can expect that it will fail every 61 years. Yeah.
So the probability.
No, and of course the MTTF is a time, but it's the inverse of a rate. Yeah. So you could say it fails once per hour. Yeah. 1 divided by hour. You take the inverse, you can say the time between failures is 1 hour. So it's that way. But again, yes, strange thing is, I was on a conference committee, and I got that publication, and as you know, I have always been looking for field data. Yes. And I was really enthusiastic, but strange thing is the other reviewers of that paper said, "Oh no, it's not interesting yet." So it was refused. Yeah. But in the end, I addressed the authors, and it was a cooperation between an American institute and a Chinese institution, and in the end, it's one of the few real field data you have on reliability of devices, and I never saw something with such a statistical basis. Yeah. So so now what we have seen is already from the curves I was providing, is the failure rate constant over time? And that is something based on what we have already seen here. Failure rate is not constant over time. We have seen it on the curves of the number of failures going towards a certain constant flow at longer times. And then you could say after longer times, evidently, it can be constant. But that will not happen until infinity, because at a later point of time, you will have wear out processes. So everybody gets older, yeah, and it gets, and the rate of aging is higher when the load on the stress is higher in that system. That's the general rule. Okay, so you could say when you look at the failure rate, we have already seen the failure rate goes down initially, and it goes somehow to a constant value. On the other hand, you have wear out processes, and that means from a certain time on, people can see that things start to fail more and more. Yeah, typically a car which has been used for 10 years, could say it's finished. Yeah, it will break down with this and that and so on. People over, let's say, somewhere over 75 or so, the rate of death is increasing. Yeah, so it's somehow it's near the end. And
I have a question.
Sorry?
I have one question again. So sorry, that doesn't seem logical to me that the failure rate is very high at the very beginning. Why is it the case?
We come to that. First of all, we just make the observation that it's the case. Yeah, it's in almost all systems. We have also biological systems. We have a high infant mortality, for instance. Yeah, some people even call it infant mortality in technical systems. So that's, first of all, it's a fact. And then we see also we have a longer time where the rate of failure, or you could also say we have in humans, we have an age between, let's say, 35 and 65 or so, where the rate of death is relatively constant. Yeah? And the question is, why is that so? And then in the end, it goes up due to wear out process. Now the question is first for the middle. You could say, okay, in the middle range, you could either say it's just failure by chance. So people 35 to 65, they rarely have, so it's not the age. They sometimes have a disease, but that's more controlled by, let's say, chance or bad luck, or they have accidents, which is also controlled by chance and bad luck. Yeah, and so in that period, if it's controlled by chance and bad luck, you can say you can model it with exponential distribution over time. And exponential distribution, on the other hand, means constant rate. But you can also come to that curve when you just have two Weibull curves. One is decreasing and one is increasing. So how's the Weibull curve? We must say f of t is 1 minus e to the power of t divided by some characteristic lifetime to the power of b. Also, we use a beta here. That's the Weibull curve. And now we have seen if the beta is 1, Which distribution is it? Then we get a constant failure rate. So it's exponential, yeah? When the beta is smaller than 1, the failure rate goes down over time. And when the beta is larger than 1, the failure rate goes up. Yeah.
In the early stages, what could be the reasons of failure? Is it like manufacturing?
Yeah, that's a good question. Let me start from the back. Yeah. So here it's failure by chance, you could say, but you could also say it's a superposition of these two curves. Yes, and that superposition is more or less somehow a constant. On the other hand, here it is wear out, so it ages, and wear out is determined by two things. One thing is how strong is the wear out process, and of course, the higher the stress is, the faster the wear out process, and the earlier it goes up with that too. You could also say when you make a stronger design, the wear out will be later, or if you make a weaker design, it will be earlier. A very simple model would be a brake pad. Make it thicker, later on brakes will be exhausted, yeah, and it will be worn out, thinner earlier. So that's an idea. The question at which time the brake pads will be worn out is not only determined by the thickness of the brake pad. For instance, if you have a driver, there was a famous race driver, starting one, the race is won on the brake. The race is not won by the accelerator, it's won by brake. So that means you drive fast, you brake a lot. What wear out is high, your brake pads. Yeah? So that means not only how it is designed, but also how it is operated. Both are in a relation to each other, and that's important. Yeah. If you build a car just for the smooth roads of Central Europe, that car will not live very long in Africa, and that's the reason why we have Land Rovers and Toyota Land Cruisers driving there. They are more rugged and they are built because in a way they can tolerate the higher stresses of the road there, if there are any roads. Okay, so that is that wear out phase, and on the other hand, we have in a production a certain portion of parts which are, you can say, defective. What's the reason? When you look at any property of a part you produce, always the property is in most cases, almost always it is determined by some Gauss distribution. So you have a range of that property. If you take, let's say, a camshaft and you test it under always same conditions, you can see sizes have certain tolerances with Gauss distribution, but also lifetimes will have such tolerances. And now, outside these tolerances, somewhere a little further outside, it's not just that the tolerance is higher, but that can really have a bad effect. For instance, lifetime is lower. Yeah? And that means due to that scatter of production quality, you always have some outliers. Yeah. You can either try to detect them by some additional measures, X-raying or such a thing, or general inspection before you sell it. But there is always something you miss, yeah. And these are the parts which will fail earlier, and the worse they are, the earlier they will fail. But when you have a certain amount of these parts in your produced sample, over time they will die out. Yeah, so the bad ones die out, and of course you could say who is responsible here. Here mainly the manufacturing manager is the responsible person, because you can have a better production or a worse production, and that means that initial failure rate curve will be higher or lower. An example in former times, quite some time ago, we had a warranty time in cars of just half a year, and then we had a warranty time which so that's not the warranty time by law, but the voluntary warranty time, and that was increased. And by German managers also, it was up to 6 years. Yeah, and you can make that when you know that the integral under the curve here is low. That's a total number of parts which are bad. And when you know that, you can determine the warranty time. Also, when you are already low here, yes, you can extend it for another 10 years or 5 years, because not much will happen, yeah, compared to that, what happened within the first year. But maybe 50 years ago or so, the German manufacturer, they withdrew from that offer, and they shortened the warranty time. Again, for me, it's a certain hint that maybe they had a little quality problem, yeah. So maybe it was too costly for them. Still, you have car manufacturers, I think from Korea, where you have the full 6-year warranty, and that means it covers the phase of initial failure rate. We have seen it in my example here. It went up to maybe between 20 and 40,000 kilometers. And then we were in a steady state or in a constant failure rate phase. Okay, that's a famous bathtub curve. It's like a bathtub, yeah, where you put in the water. It's deeper here where you lie with your back. It's a little flatter, and in that way, it looks like the length section of a bathtub, and so it got its name. Again, every engineer should know about the bathtub curve, but not alone that, but also what are the reasons for that curve, and what is also important, how can we describe it? And we can describe it with 2 or 3 different Weibull distributions. 2 is sufficient, in most cases sufficient, but the beta value, which tells us, is it constant, is it increasing or decreasing failure rate, is different. Okay. I also made a table on that, but in the end, I already told you that, so it makes no sense going through it in detail again. In fact, one of the big studies we had was by the Bosch company. There was a dissertation, Mr. Pauli, in 1998. And for instance, also he had a databases not as much as the Chinese, but already 10 million electronic control units. And he stated that 100 out of 1 million will fail in 10 years. And also he assumed a Weibull distribution. He didn't take into account wear out phase. Yes, he only had the first and second phase, and so he ended up with a beta value of 0.5. And you can keep in mind a beta value of 0.5 is very representative of early failure. Yes. And that Pauli, he also found in his dissertation that the failure rate will double when you increase the temperature by 25 to 30 degrees. Normally, you would expect more, but you also must keep in mind that there are very many not more, but doubling in a smaller temperature range. So that temperature has a stronger effect. If temperature alone is doing that, then it's true, but you also must keep in mind that in real automotive applications, we have many failure causes, yes, and so that means and also many stimuli which lead to degradation, and in that way, for instance, vibration also, temperature is not the only effect we have here. But that again was, you could say, hard data from the field. I would say the application range was similar like in my investigation, and in fact, I must say, by that dissertation, I also was inspired a little, because I said, okay, my team is working on reliability of electronics, but we don't have these data, and just by chance, one of our business units came and said, we have a problem with this anti-brake locking system, ECU. And so just by chance, I got the data, yeah, for my part of what you have seen. And okay, that's another thing also quite some time ago, unfortunately. I later on have to show you the film. That is a power electronic device. So at the end of the 1990s, we were starting with development for electro vehicles. Yeah. So in fact, that was semiconductor. We even built a smart car, which was an electrical car, and that was from our test bench. We were looking for a power cycling capacity. So how many millions of power cycles can that thing tolerate? And suddenly the device, it flashed, you could say, in the temperature camera. And after the flash was over, there was a big hole in the semiconductor. Of course, it was dielectric breakdown we had here, and so in that way it was a failure. Other things which we found in electronics when they had failed is, for instance, cracks here. Yes, I already told you about intermittent failures due to thermal problems. Such a crack is a very good source of intermittent failures. That also was from a small power semiconductor. Here, that is something, ceramic chip capacitor. Chip capacitors are a part that can be risky. So again, it's very much depending on the batch that was produced. You can have decades where you have no problem, but if someone does something wrong in production, these can be very sensitive against stresses. And what is also not liked very much by these devices is, for instance, very high cooling rates. So that soldering also has a certain effect. In the end, they do not really fail. Unfortunately, they tend to fail when the board is with the customer and when it's in operation. That was another thing also for power semiconductors. That was a new technology. And here is something that is really strange. That was a new technology and that tolerated many cycles. But what is strange, we had simultaneously three failure modes, which were all, let's say, competitive against each other. That's normally not the case. When you have a wear-out process, in most cases, you could say it's one thing. For instance, here are the bonding wires, and due to the CTE mismatch, the bonding wires lift off. On the other hand, we have a CTE mismatch between the copper and the silicon, and that leads to cracks here in the die attachment, which is silver sintering. And also we have cracks here in the copper. So you could say that part was more or less finished under all aspects. That was really worn out, and not only with one failure mode, but with three failure modes simultaneously. So that was temperature or power cycling. Then we have something that is also interesting. That was also something that happens and leads to intermittent failures of faults. That's that's corrosion. And here we had parts which were tested under climate, and the climate was 85-85 test. The 85% humidity and 85° centigrade. So my question is, when you look at the humidity in a room, so that means the air has a content of water. And the content can be maybe between 0, which is dry air, and 100%, which is when you have fog already. Then you can have even more, but as long as it's still just the air or just when the fog starts, you have 100%. So condensation, that means precipitation of liquid water. At which humidity content will you have it? By which humidity is the dew point defined? Yeah. When you have air in the room, and you can have variable moisture content or humidity, or relative humidity, better, which can be 0 to 100%. At which humidity will you have precipitation of water? That means you see fog or something. So go into the bathroom, you come out from the shower, your mirror misty, and so what's the humidity in your room? Sorry? 100%. That's what you normally think. in reality, in technical systems, it's below 100. The reason is that we have impurities and we have rough surfaces. And here, at absorption of water and even formation of a water film will be present. And what is also important, for instance, iron. Maybe you also know the term, it's a hygroscopic substance. Yeah? For instance, you have salt, and in former times, salt always became cloggy, yeah, because it took up humidity. Yeah? So you put in a grain of rice, for instance, dry. So that means when you have such hygroscopic materials, then you can have precipitation and formation of the water film below 100% of humidity. And here, the following thing could be observed. These devices, which again were ECUs, they were operating for some time in that moist environment, it was in the test environment, and suddenly they had a fall. They were reset and working again. And after some time, the same thing happened again. And then my colleagues took them out, and we took them in a microscope and in a scanning electron microscope, and we were seeing certain structures, which is here like such a small, you could say, tree, yeah, or like a branch of a pine tree or so it looks like, yeah, here. And what could that be? It also was found on top of the devices, and it always seemed to start from many positions where there was solder material. And then in an electron microscope, we could also have microanalysis. And then we find the following elements: tin and lead, that's from the solder. We find silicon, that's from the glass fibers of the printed wiring board. And then as magnesium and aluminum, that can be from some other metal parts. In fact, I don't know. But what is important, we have here chlorium. It seems not much, but it's sufficient. And when you have deionized water, it doesn't conduct electricity. Yeah. So if you have fog, it is deionized water, or even distilled water, you should say, that is non-conductive because it has no or not many free ions that can move. What happens when you put in sodium chloride? Yes, it's conductive. You have ion conduction. And that's the reason why then we first had a thin film of water, and in that film we had some kind of, we could say, electroplating or electrodeposition process. Of course, in such an ECU, you have a voltage of 0 to 12 volts or 5 to 0 volts, but we have some voltage differences, and these lead to some electroplating. So the combination of dissolution of tin and lead in that water film, the migration of that ions in the electrical field led to the deposition of new tin and lead at the tip of these so-called dendrites, these trees here, yeah? And these trees were growing in this direction, and when they had close to contacts, they just evaporate. But of course, the processor doesn't like that, so you reset them probably, and in that way, you get a fault. It's not a failure really, because after that it will work again if you reset it. But in the end, you could say that was a very good example of corrosion-induced failures. In fact, I presently have a PhD student in Bosch who is precisely addressing the conditions leading to such tin tree formation. So that's really an important problem. Partly it can be avoided by putting on a conformal coating, a varnish on that board, but that only partly solves the problem, because water also diffuses into the polymer and then precipitates under the polymer. Okay, so what we have seen today is data on what the probability is of failure of electronics, how we can describe it, what influences we have, what are probability curves and probability models we can use for that, mostly based on the Weibull distribution. And also we have already seen some examples how it can fail. Okay, thanks for your attention.